Hi, my name is Litya and my metric number is 163850. We are from Group 12 presenting our CPC451 Assignment 2 titled Word Count Implementation using Hadoop MapReduce. First, let me explain big data and its challenges. Big data refers to huge data sets that a single computer cannot process efficiently. There are three main challenges. Volume means there is too much data, terabytes or even petabytes. Velocity means data arrives too fast and needs real-time processing. Variety means data comes in different types. This includes structured data like spreadsheets, semi-structured data like JSON files, and unstructured data like text files, images, and even videos. To solve these big data challenges, we use Hadoop. Hadoop is an open source framework for distributed storage and processing. It has three core components. First, HDFS stores data across multiple machines with replication so that the data is safe even if a machine fails. Second, Yarn manages CPU, memory, and schedule tasks. Third, MapReduce processes data in parallel across the cluster. MapReduce is a programming model introduced by Google in 2004. The pipeline has 7 steps. Input stores raw text in HDFS, split divides the file into chunks, map emits word and one pass, combiner does local aggregation to reduce network traffic, shuffle groups the same words together, reduce sums the counts and outputs word and total count, and finally output saves the final word counts to HDFS. Now let me explain the problems we are solving and our objectives. First, traditional methods cannot process large files. Second, we need to read, split, and clean input text. Third, word occurrences must be counted. Fourth, the MapReduce job needs proper input and output configuration. Fifth, network traffic is heavy without local aggregation. And sixth, the program must be tested with sample files. To solve these problems, our objectives are as follows. First is to implement distributed word count using MapReduce. Second, create a mapper to tokenize and clean text. Third, create a reducer to sum word counts. Fourth is to create a driver to configure the job. Fifth is to use a combiner to reduce network traffic. And finally, we need to test the program with sample1.txt and sample2.txt files. That's all from me. Thank you.
Hello everyone, my name is Kavitashini and my matrix number is 164329 and I'm going to explain about the methodology. Let's start with our environment. We ran a pseudo distributed Hadoop setup on Ubuntu 24 where the name node, data node and yarn all run as separate Java processes on a single host. This stimulates a real cluster without needing multiple machines. Our software stack is Hadoop 3.3.6, Java JDK 11, and Apache Maven for building and packaging our JAR. Configuration was handled through the four standard XML files, HDFS, Mapred, and Yarn, with the replication factor set to 1 since we are on a single node. The project is organized cleanly: source files for the mapper, reducer, and driver, input text files, and a pom.xml for Maven. Moving to the mapper, the word count mapper takes each line of text as input and outputs word one pass. It does this in 5 steps: first, converting the line to a string, then stripping punctuation using a regex, lowercasing everything for consistency, tokenizing by spaces, and finally emitting each token as a key value pair with a value of 1. The time complexity is O(n) per line, where n is the number of words. By handling all normalization here in the mapper, we keep the reducer as simple as possible. The reducer receives each unique word alongside a list of ones collected from all mappers. It simply sums that list to produce the final count. For example, the word Hadoop appearing 6 times arrives as the list 111111 and the reducer emits Hadoop and 6. A key design choice here is we reuse a single int writable object rather than creating a new one per word, which reduces garbage collection overhead. Time complexity is OM, where M is the number of unique words. Finally, the driver wires everything together, registering the mapper, reducer, input and output format, and configuring the job. Crucially, we also set the combiner class to the reducer itself. This is valid because word count is both commutative and associative, meaning we can safely aggregate locally before the shuffle phase. The results speak for themselves. The mapper produced 341 pairs, the combiner reduced that to 177 records before they ever hit the network, a 48% saving in data transfer. And since we reuse the reducer as the combiner, There's zero extra code to maintain. That's all from me. Thank you.
Hello everyone, I'm Darshani Tasrua and my matrix number is 164062. Our job executed successfully in pseudo-distributed mode on a single node. We use sample 1 text file as input, which is 2.27 kilobytes containing 31 lines of text. The entire job completed within 15.09 seconds using one map task and one reduce task. Looking at the performance metrics, the map phase processed 31 input records and produced 341 intermediate word pairs. This is where the combiner optimization came in. It reduced those 341 records down to 177 records, achieving 48% reduction in data before network transfer. The final output contained 177 unique words. Here are the top 10 most frequent words. The appears 18 times, which is expected in English text. More importantly, Hadoop appears 15 times and data appears 14 times. This confirms that our input text focuses on Hadoop and big data processing. The top 4 words alone account for nearly 18% of our all word occurrences. This slide summarizes four key MapReduce optimization. First, parallel processing allows multiple mappers to run simultaneously. Second, data locality moves computation to where the data resides, reducing the network traffic. Third, the combiner gave us a 48% reduction in network traffic as shown by our 341 to 177 record decrease. Fourth, fault tolerance automatically re-execute failed tasks. The key takeaway is that the combiner alone cut network traffic by nearly half. Identified for limitation. First, small file inefficient means Hadoop's overhead exceeds processing time for tiny files. Second, no stop word filtering, so common words like the dominate results. Third, we use single node cluster, so true parallelism wasn't tested. Fourth, no stemming, so words like computing and computation are counted separately. From this, we learned that MapReduce is simple conceptual, but data flow requires careful design. The combiner significantly reduced network traffic. HDFS overhead can exceed processing time for small files. Text normalization affects correctness, and yarn latency makes MapReduce suitable for batch jobs and not real-time queries. Finally, the word count pattern powers many real world applications. Google uses it for search engine indexing, Netflix and AWS use it for log analysis, LinkedIn and Netflix use it for recommendation system, and it's used NLP tasks like sentiment analysis. In conclusion, we achieved a 48% combiner optimization, identified 177 unique words, and demonstrated parallelism, data locality, and fault tolerance. Future work includes adding stop word filtering, stemming, and deploying on multi-node cluster. That's all from me. I will pass it to the next member. Thank you.
Good day, Doctor. I'm Tejashri and my metric number is 163506. Today, I'll be demonstrating our how to map reduce word count implementation for assignment 2. So let me start by running the program. First, the script checks if Hadoop services are running. It verifies if the nodes are running using GPS. Next, it creates the necessary HDFS directories, specifically the import directory where our text files will be stored. HDFS is Hadoop's distributed file system that splits data across multiple nodes. Now, all text files from the local input folder are uploaded to HDFS. This is important because MapReduce can only process data stored in HDFS, where it can be distributed across the cluster. The program now compiles the Java code and packages it into a jar file using Maven. This jar contains all three components of our MapReduce job. Once the jar is built, the program displays all available files in HDFS and asks the user to choose which file to process. For now, we have two input files, so let me select file number 2. After selection, it shows detailed information about the chosen file, like the name, size, and its HDFS path. Step 1 is the input phase. The file is loaded into HDFS. The system counts the number of lines and displays the file size. This data will be split into chunks and distributed to different mapper nodes. Step 2 is the map phase. This is where the core processing begins. The input is split into chunks. Each mapper takes a line of text and tokenizes it into individual words. This phase does three things: removes punctuation, converts everything to lowercase for normalization, and then emits key value pairs, where the word is the key and the number 1 is the value. Step 3 is the shuffle and sort phase. This is automatic in Hadoop. It transfers all the key value pairs from the mappers to reducers. All pairs with the same word are grouped together and sorted alphabetically. Finally is step 4, which is the reduce phase. It receives each word and an iterable list of all the ones associated with it. It sums them up to get the total count for the word, then writes the final word total count to the output. Now we see the actual results. The program displays each unique word alongside its frequency count. Notice the color grading. Words with higher counts appear in red or yellow. Here's a summary: total unique words and total word occurrences in the document. The program also shows the top 10 most frequent words. This gives us insight into the most common terms used in the document. Finally, we see the job execution summary with total execution time, map task completed, and reduced task completed. That's all from us. Thank you.